In this video, I want to continue our discussion of orthogonal projection operators and their properties. And we're also going to define a orthogonal projection operator, which is an orthogonal projection operator onto the column space, which is perpendicular to the column space of X. So just to remind ourselves, the idea here is that we have some vector Y, and we'd like to project it onto the column space of X, the column space of our independent variables. And we've spoken about how the projection operator Px is a way of projecting from Y onto the column space of X, and that gives us mu out or mu hat out. Another property which we can sort of see that the projection operator should have is that essentially if I apply the projection operator to something which has already been projected onto the column space of X, so assume that we have some vector Z and we project it onto the column space of X, and then we do the projection of that onto the column space of X, well, essentially that should just yield out Px times Z because we've already projected it onto the column space of X. Let's just check that this is actually the case. So if I operate Px on Px, then I'm just going to get X times X primed times X to the power minus 1 times X primed, and then we just have the whole thing again. So we have X times X primed X to the power minus 1 times X primed, and we're operating on some vector Z, which in general doesn't lie in the column space of X. So here straight away we can see that this term here is just the inverse of this term here. So these two terms just disappear and just yield the identity matrix, which then just passes through everything else. So then we're just left with X times, we're going to have X primed times X to the power minus 1 times X primed of Z. And that straight away we can just see is just the original projection operator times Z, or operated on Z. So this particular property, which we've just proved for the orthogonal projection operator Px, is what we would call the operator being idempotent, or the matrix as being idempotent, which means that if you operate it on itself, it just yields itself. In this video, I want to also talk about the projection operator, which is defined by I minus P of X. And let's talk about what properties this will have. If we're talking about a vector Z which lies orthogonal to the column space of X, so that's, let's say, some vector which we're defining here, Z, then what will this particular expression here yield? Well, we know that since, or if we expand out this bracket first of all, we're just going to get Z minus P of X times Z. And we know that P of X times Z, if Z is orthogonal to the column space of X, it's just going to be 0. So this second term here is going to disappear, and we're just going to be left with Z. So, okay, so this operator, whatever it is, applied to Z, if Z is itself orthogonal to the column space of X, so we can sort of write that as column, and then I'll put this sort of inverted T here to represent the fact it's orthogonal to the column space of X, then this operation onto Z just yields Z. And then if we think about the circumstance where instead Z is actually in the column space of X, so that means it's orthogonal to the column space which is orthogonal to X, that means that we're going to have I minus P of X times Z is then going to be equal to, we're just going to have Z minus P of X times Z, and if which the circumstance which we're dealing in here, Z is actually a member of the column space of X, then this second term is just going to be equal to Z minus Z, because if it's already lying in the column space, the projection onto that column space is just itself, which means we're going to have 0 here outputted for when we operate using I minus P of X on Z. So we can actually think about I minus P of X as representing an orthogonal projection operator, right? Because we found that when we operate it on a vector Z which lies within the realm which is orthogonal to the column space of X, we just get Z out, which is what we expect. And then when we operate it on a vector which is orthogonal to that particular column space which is orthogonal to the column space of x, then we get 0 out. So we can think about I minus p of x as actually being an orthogonal projector, but onto the space which is orthogonal to the column space of x.